John, you're Professor of Materials for Energy. Can you tell me a little bit about that job and how you got into this area of research?
Yes, I joined the Open University in 2008, and that was after 30 years working in industry, in aerospace and the nuclear power generation industry. I worked there as a mechanical engineer, but with specialist expertise in structural integrity, by which I mean designing against failure. You can imagine failure is very important in the nuclear industry. And I'm interested in the aspects of structures which contribute to failure. For example, residual stress.
So when you say design against failure, what kind of things fail and how?
Oh, well, in the nuclear industry, you don't want anything to fail. But from time to time, you do find cracks can appear, unexpected degradation, which could be owing to corrosion or fatigue or other unexpected circumstances. And my role there was understanding why these defects and cracks developed, and then improving the assessment methods so that these could be predicted and managed in a structured way.
So what kind of components fail? And I'm guessing that we've got a part of a component here, this large chunk of metal.
Yeah. Well, this piece of metal was extracted from a nuclear power station, and it's actually part of a steam header. So this is a vessel containing steam collected from boiler tubes at a nuclear power station. And what's interesting about this sample is that there is a crack about 10 millimeters deep, just adjacent to this large weld here.
Oh, I can see it.
Now
that's slightly concerning. Cracks in nuclear power stations.
Indeed, yes, which is why this component was extracted from the plant, but they wanted to investigate as to why did that crack develop, and what can be done to mitigate future cracks of that kind, and where else might it be you get this type of cracking in nuclear power plants. Now, in fact, this crack was driven mainly by hidden residual stresses which are locked into the structure during manufacture. So the welding process, which you can see this very large weld here, is a very aggressive, heat-intensive process which can introduce very large strains and stresses. And it's the relaxation of those stresses which is actually causing this crack to appear by a mechanism called creep. Okay. Now, creep is something which happens at high temperature, slow deformation, but you can develop within the material cavities and micro cracks which can join up to create a macroscopic crack like this.
So that's a residual stress? That's a result of residual stress?
That's a result of residual stress, right. Yes. And it can be worse. I mean, I do remember a pipe at a nuclear power station which developed a leak. So a crack had propagated all the way through the thickness. And that's, of course, undesirable for nuclear safety point
more
of view.
than undesirable,
yes.
I would imagine.
Yes.
Okay.
Well, if it leaks, at least you know that you've got a crack.
Yeah.
What you don't want is a break,
yeah.
A complete guillotine break.
Yeah. You've got another sample,
yes.
Which is slightly more organic than this one. Do
Well,
you want to talk me through
yes,
that?
you not only get residual stresses hidden within man-made structures, but you also find it in nature. And so we've got a rather nice example here of a demonstration of residual stresses in a stick of rhubarb, okay. Which I cut fresh this morning. Okay. And I'm going to demonstrate how if we cleave this stick yeah. Down the centre, okay. That we'll see what happens.
Okay, go for it.
So here we go.
Don't slice your fingers at the same time. Very, very neatly done.
Not exactly. And what you can notice is that the cut parts splay yeah. out. So they no longer match. And there's a displacement mismatch yeah. of the order of 20 to 30 millimeters at the bottom and similar at the top. And it's that deformation which has been released by, or used to release the residual stresses, which has resulted in this deformation.
So that's residual stress in rhubarb?
Yes.
Okay. Well, I'm guessing that you don't work on rhubarb that often, so what kind of components do you look at? What kind of things does industry send to you here at the labs?
Well, this actually illustrates the principle that if you cut a component with residual stress inside into two parts, the cut faces deform. Right. So we've actually adapted this sort of technique, or at least we implement this type of cutting technique on metallic components to find out if there's any stress inside. And we cut metal not by a knife, but using a technique called electro-discharge machining. Now this technique involves a very fine wire, which may be about 1/4 millimeter diameter. And this is a very fine wire. It's made of brass. And you pass pulses of electricity through the wire. Now these pulses then create sparks between the wire and the workpiece. And there may be thousands of sparks generated. Now each spark evaporates material around the wire, and it's this evaporation, we get lots of tiny pits.
So it vaporizes the metal?
It vaporizes the metal,
right.
Yes, and the wire advances and you can cut the entire component. Now this technique is actually very precise because these pits are very tiny, so you can get a very fine finish in a very controlled way.
So once you've got the cut piece, how do you then measure and look at and quantify the residual stress in it?
Okay, so we then have two cut parts, and we take each cut part and measure the deformation, the shape or the contour of that cut surface. And we do that in a metrology lab with a coordinate measurement machine.
Okay, you're going to show me that next?
And I'll show you that next.
Okay,
yes.
lead on. So this is where the cut components end up?
Yes, indeed. And here we have a very large component, and it's part of an offshore wind turbine, the gear wheel from the turbine house. And this top surface has been cut by wire electro-discharge machining using the machine you've just seen. And what we're doing here with this coordinate measurement machine is that it's actually measuring using a laser probe. You can see there's a red spot there.
Oh, yes, yeah.
And it's measuring the topology, the deformation actually of this cut surface.
Right.
So it's acquiring many thousands of data points. So we'll get a cloud of data associated with this cut surface, and this which will define the contour.
Oh, like a contour map of the
exactly,
surface?
Yes. So that's a deformed surface. And then we apply that deformation to a virtual computer model and carry out a stress analysis which will give us, from which we can infer a map.
A stress map?
Of the stresses, yes, which are acting normal, perpendicular to this cut face.
Right. So that will show any residual stress which can then be manufactured out in future components?
Well, it will tell in this component what that stress state is, and they will then compare it with some predictive models of what they think is there. Right. And then that will help them to understand, the reasons for the failure of this wheel.
So presumably your research is useful in industry?
Well, this technique which we implement here is quite cheap, it's quite quick, and it gives you a map of the stresses. And so industry are very interested in this, in measurements using this method. So much so that we've had many requests for measurements, and we've set up an internal business unit providing a commercial measurement service.
So that's your research, and that's the work that you do for industry. How does it then feed into teaching at the OU?
We have taught courses on things like structural integrity, and understanding residual stresses is very important part of that teaching material, including measurement of stresses using techniques like the contour method. And it gives you this visual picture of what's going on. So it's actually a very useful technique to illustrate and to underpin the mechanics which we're teaching in our courses and modules.
John, thank you very much. It's been fascinating being guided around your labs.
Thank you.